Hi, I am Mikela Pryor. I received my bachelor's in biosystems engineering from Florida A&M University, and I'm now a master's student at Texas A&M University. I've been working under Dr. Fuad Jaber, and in the future, I hope to earn a PhD and work to reduce flood risk in communities of color and increase their access to green space, especially in my hometown of Dallas, Texas. Thank you for having me, and I will be presenting my work on the design and public perception of a bioretention area in Dallas, Texas. And let's get right into the intro and background of the work. The 5 Mile Creek watershed in the Oak Cliff neighborhood of Dallas, Texas is 70 square miles with a population of 186,297, 61% of which is African American. According to hydrologic models, Dallas neighborhoods south of the Trinity River, which bisects the city, have experienced frequent flooding. 5 Mile Creek runs 70 square miles, part of which is Alice Branch. The Alice Branch runs behind South Oak Cliff High School, as well as residential homes, apartments, and a healthcare facility. Part of a renovation for Alice Branch is an accompanied park space, Anchor Park. A feature in the park design is bioretention cells, which will help mitigate flood risk and reduce the runoff loads to the creek, which I'll further explain in a little bit. Migration into urban areas is projected to accelerate in the future, contributing to increased development in urban environments. Impervious surfaces, including paved roads, buildings, parking lots, they're all a staple feature of continued development, and they prevent infiltration, leading to increased runoff volumes and pollutant loads. Traditional stormwater measures collect runoff in a decentralized approach, leading water away from urban areas and into basins and streams. A lack of infiltration collects pollutants while also decreasing groundwater recharge and increasing peak flows. Green stormwater infrastructure, also known as GI or GSI, takes a more centralized and connected approach to stormwater management, and instead of curbs, gutters, manholes, and pipes, engineered soil and vegetation is used. These systems capture pollutants and decrease runoff volumes, primarily due to their infiltration capacities. This stormwater measure includes, but is not limited to, green roofs, rainwater harvesting, bioswales, and bioretention cells, which are the focus of this study. Bioretention, a fairly recent approach to stormwater management, is a vegetated infiltration practice that includes a layer of soil, sand, organic media, creating internal water storage with supporting vegetative layer on top. The studies that have been conducted show a wide range of success rates for water quantity reduction, reporting 24 to 99% peak flow rate reductions and 20 to 98% of volume reductions, which leads us to further speculate how they can be optimized. Many cities have developed climate change and stormwater management plans that include GSI, but barriers to implementation persist. Such barriers include a lack of awareness of GSI from the public and its benefits, as well as national and local engineering design standards. This leaves landscape designers and engineers with little guidance on how to optimize design for their local areas, especially in a regulatory context for compliance. Locality of standards, which can be informed by performance evaluations, can better determine the specifics of the design that optimize the performance of the GSI, especially for improved nutrient loads. Another large barrier to urban green space planning is spatially based social valuation methods, such as individual perceptions, preferences, and non-monetary values of environmental features. Both of these barriers are addressed in the study. Now on to the research questions. This work seeks to understand whether a bioretention area can be designed for maximum pollutant removal and runoff reduction in Dallas. On the social side, we want to understand the awareness of the public with regards to GSI and its benefits. Does the public even see value in GSI, and what kind of value? And what factors contribute to the willingness to implement GSI on behalf of the public? These questions form the methodology of the study. Now on to the methods and materials. The design of the 2 bioretention cells consisted of a site selection, catchment area determination, and bioretention area design. Deciding what area of the park to place the cells and how many cells were needed was determined by the area of the entire park, and viewing the topology of the land. Where did water naturally pool? Since the park was about 5 acres, 2 cells were designed. The SCS curve number method is shown here. The curve number is a land use and soil type factor that reflects the imperviousness of the ground surface. Bioretention area design, being the size of the actual cell, was accomplished through cell surface area calculation and drainage sizing. The cell surface area calculation was done by calculating volume of runoff divided by volume per square foot. The drainage pipe sizing was done using the Darcy and Manny equations to calculate the first flow and then diameter of the pipe. For public perception studies, a literature review was conducted using TAMU libraries and Google Scholar to find public perception studies on green infrastructure for stormwater mitigation. The following keywords were used in the search: green infrastructure, stormwater, perception, and environmental quality. From the search results, 31 studies were selected and reviewed in a literature matrix. The definition of green infrastructure was found in each study to ensure that the definition related to treating stormwater instead of just green space. Research questions, possible barriers to GSI implementation, conceptual framework, methodology, survey questions, and results and conclusions were extracted to find a correlation in the literature. And here are the results. These are the flow and sizing calculations for the SES curve number method and calculation of flow for sizing. 512 and 219 cubic feet were the resulting sizes of the cells. They were designed to store 12 inches of water stored in 1 square foot of retention. And this is what the final site will look like with the bioretention cells in blue. The bioretention cells encompass a mixture of 50% clear sand, 25% yard compost, and 25% in situ soil to offset the clay soils in the Dallas area. It is expected that the bioretention cells will effectively reduce runoff volumes as well as pollutant loads. Nitrogen removal is somewhat variable as a design standard has not been widely accepted to optimize its reduction. Most literature suggests that nitrogen fixing plants will optimize the removal. This is the conceptual framework we developed for the public perception study. We classified our independent variables by socio-demographic variables, prior environmental knowledge, and perceptions of existing environmental conditions in order to answer the research questions. The dependent variables will be perception of green infrastructure and willingness to implement green infrastructure. And here are the questions we decided to ask in the survey. The final survey design inquires about: number 1, valuation of bioretention, bioswales, green roofs, permeable pavement, rainwater harvesting, and rain gardens, and their perceived importance for water quality, rainwater retention, visual attractiveness, and recreation. Number 2, personal experience with flooding and water quality in the area. Number 3, park usage. And number 4, demographics. Since the bioretention cells are placed in a park space and there's a lack of literature on GSI in park space, we wanted to ask questions on their park usage as well. And our next steps. Plant selection will be done to optimize nitrogen removal. Studies show that this is the most difficult to optimize out of all the pollutants. Bioretention cells will finish construction in January, as it was delayed due to the pandemic. Distribution of the survey will occur during the fall semester virtually, as this was also delayed due to the pandemic. And post-construction surveys will also be given. 2 to 3 months of monitoring will occur after the construction following rainfall events. In conclusion, the study will be used as an education tool to teach residents and stakeholders about green infrastructure and its ecological services. The survey will be used to increase the knowledge gap concerning public perception of bioretention, especially in parks. The performance evaluation and monitoring will increase the body of research on the benefits of green infrastructure and how they can be implemented effectively with community input. This study shows how community members best want to be served concerning green infrastructure. And I would also like to acknowledge the following, and thank you for allowing me to present.